Okay, so today our speaker is Maria Vyshegorodtseva, and she will tell us about dynamical entropy. Please.
Yes, one moment. So, do you see my screen at the moment?
Yes.
Okay. So, excuse me. Yes. Excuse me. I will use my full screen mode. So today I would like to tell you about dynamical entropy, and my talk will be heavily based on the book, the name of which you can see on your screen. The book is called Dynamical Entropy in Operator Algebra. It was written by Sergei Nishveyev and Erling Stormer, and published in 2006. So the idea of this book is so the first several chapters are about um, how we can. So they tell us how we can generalize dynamical entropy to non-commutative operator algebras. And in my talk, I would like to start with the beginning of this book, and firstly, we will just define some. So we will start with some basic definition, and probably a lot of you will know many things from this first presentation, but I think that in several weeks I will make a second presentation which will take us further in this topic. So, and we will start with defining a measure entropy on finite partitions of a Lebesgue space. So firstly, we take a Lebesgue space, and we will need X to be a metric space. We want it to be separable, and mu is a standard. We want mu to be a standard probability measure, and B to be a sigma algebra of Borel sets. So then we take a finite partition of this space and define the entropy of Xi, this partition, as the following function that you can see on your screens. And here, function eta is defined as follows. It is defined as minus t logarithm t if t is greater than 0, and it is 0 if t is equal to 0. And we should remember, it will be very useful for the talk, that this function is concave, is strictly concave, and that it is equal to 0 if t is equal to 0 or 1, and only in these two cases. We will sometimes denote measure entropy as h mu xi, or just as h xi. So this is our basic definition, but we would like to define conditional entropy. So we will take another partition of X and call it zeta, and then if zeta is an uncountable partition, we would like to so if that is an uncountable partition, we would like to when that is uncountable, then the quotient space X factor zeta is again a Lebesgue space, and the reason for that is that only a countable number of elements of a partition zeta can have a measure that is greater than 0, and therefore when we factorize this when we factorize the space X, we will get a countable number of points, and the union of these points will have measure 1, and therefore we will get so, and therefore we will get that factor xz is a separable space, and so it is easy to see that x factor z is a Lebesgue space, and then we would like to identify the complete sigma subalgebras of B with spaces L infinity x factor z mu, and so it is quite easy to see this correspondence because we take so firstly we will consider this subalgebra of beta that is excuse me, как порождается на английском?
Generated.
Yes, thank you. Sorry. So we will take a subalgebra generated by a partition zeta, and then we will take the functions that are constant on the elements of this algebra, and create the correspondence of this subalgebra of L infinity x mu with the algebra L infinity x factor z mu. So then we would like to define a conditional entropy. So this is a measure preserving map that you can see on this slide, and Ez is determined by the condition that the integral of Ez from f times g is equal to the integral f g d mu for f from L infinity x and g from L infinity x factor zeta. Then we define the conditional entropy as follows. I think I won't read it out loud, so you can all see it on the slide. Y denotes the characteristic function of a subset of x here. Then we will see what happens if in this definition we will take a finite partition zeta. So here we assume that zeta is a finite partition, and therefore we can write the definition of conditional expectation as follows, and so this is just a sum from 1 to m of the fraction mu from f times the characteristic function of yl, and we divided by mu from xa. So here mu from g, the measure of g, is the following integral that you can see. And therefore we derive the definition for conditional entropy. So if if we take a trivial partition nu that is the whole x, so we just take a partition that consists of one element, then the conditional entropy is equal to the entropy of X. So, and for two partitions X and Z, we define the relation, which in Russian is called меньше по включению. Вы не могли мне подсказать, как конкретно переводится? Меньше по включению?
Yeah, я бы сказал, less than or equal to.
Excuse me?
I don't think there is a special word. If you say that xi is less than or equal to zeta, then this will be okay.
Okay, yes, xi is less or equal to zeta if each element of the partition xi is the union of some elements of partition zeta up to a set of measure 0, and this means that this algebra L infinity x factor xi lies in algebra L infinity x factor zeta. We would like to define the operation, which I will call the sum of the partition, I think, or the union of the partitions. Let's call it the union of partitions. The union of partitions xi and zeta consists of all the intersections of the elements of partition xi and zeta, and for a collection of partitions, we just take all intersections of all the sets of all the partitions, of all the sets that are inside this collection of partitions. So then we would like to discuss the properties that hold for conditional entropy. So firstly, conditional entropy of xi with respect to zeta is greater or equal than 0, and the equality holds if and only if xi is less or equal than zeta. The second property is that we can rewrite the conditional entropy of the union of xi and theta with respect to zeta as in the following form: the conditional as the sum of conditional entropy of xi with respect to zeta and conditional entropy of theta with respect to xi and zeta. Also, the conditional entropy of xi with respect to zeta is increasing in xi and decreasing in zeta, which means that when we take xi 2, which is greater in this sense than xi 1, then the conditional entropy of xi 2 with respect to zeta is greater than the conditional entropy of xi 1 with respect to zeta, and is decreasing in zeta, which means that if we take two zetas, zeta 1 and zeta 2, and zeta 1 is less or equal than zeta 2 in this sense, in the sense I discussed before, then the conditional entropy is decreasing. And from these two properties, we can derive that entropy is a subadditive function. To do this, we firstly achieve the following inequality, which is very easy to check. We just you firstly apply the second property, and then we see that the union of two partitions is greater or equal than each part of this partition, and therefore we achieve this result. And secondly, we just use trivial partitions as zeta and epsilon and achieve the subadditivity of this function. Okay, I think that I will prove these conditions, but a bit later, and when I will use the whiteboard to write everything down. Then we are moving to discussing the entropy of dynamical systems. So firstly, we define a dynamical system, which is so here we have a Lebesgue space X and the probability measure mu, and we take a map T, which is a measure preserving and vertical transformation of X. We would like to define a topological model of the triplet X mu T as another dynamical system Y, sorry, Y new S, and here S is a homomorphism of a compact metric space Y, and nu is an S-invertible probability measure, and we say that this triplet is the topological model if these two triplets are isomorphic. So there is a statement that a topological model of dynamical system always exists, but so, and to see this, we should take the spectrum of any weakly operator dense invariant separable C star subalgebra of L infinity X mu for Y. But to be honest, I was thinking about this place in the book, and I haven't figured out how to construct this topological model. So probably if you have questions about it, probably somebody else can, I mean, among our listeners, maybe somebody understands this part, or if you would like me to try to dig inside this, I can prepare this for the second part of our talk.
So the question is the existence of such a subalgebra, if I understand you correctly. So, well, that's an interesting question. Maybe indeed you can explain this in your next talk. Why such subalgebra exists? Okay.
Okay. So now I would like to proceed and consider a dynamical system and define an entropy of T and X. So firstly, we define a dynamical entropy for a pair T and a finite measurable partition. And we define this entropy as follows. We define it as a limit of 1 divided by n from times h from the union of a partition and n minus 1 images of this partition. So the image of a partition is just an image of each of the parts of this partition, and it will exist because of the subadditivity of entropy, and a well-known fact that when we have a sequence of real numbers, such that and n plus mth element of this sequence is less or equal than nth plus mth elements of this sequence. And so if we have such properties, then the sequence divided by n exists and coincides with the infimum. So this is why the entropy of, so this is why this limit always exists, and the definition of entropy of dynamical system is correct. And next, we would like to define the entropy of T as a supremum taken over all finite measurable partitions of X mu. But unfortunately, this is not the greatest way to define entropy, because it is not very practical to compute this supremum. And therefore, we would like to define it in another way. So firstly, we would use a lemma that if we have two partitions psi and zeta, which are finite, we have this result that h of psi and t is less or equal than the entropy of z and t plus entropy, then plus conditional entropy of psi and z plus minus, where z plus minus is the union of all images and preimages of zeta. And a measurable partition, psi, is called generating if psi plus minus is the partition of x into points. So from the lemma that I have written in the beginning of the slide, we achieve the following result. We achieve a theorem by Kolmogorov and Sinai that if psi is a finite measurable, is a finite generating partition of a dynamical system, then the entropy of this dynamical system is equal to the entropy of this partition and T. So we just have to compute one. We just have to compute one entropy of psi and T, and we achieve the entropy for this dynamical system, and we don't need to take the supremum of all possible partitions. So now I will discuss an important example where we can easily define a generating partition, and this important example is the Bernoulli shift. Firstly, let us define it. Well, we will define a Bernoulli shift with weights. So firstly, we will take a set of n numbers, and we will define nu as a probability measure in these numbers, and the probability of choosing number k we will call lambda k. Then we will have a word which is infinite so we will have a space of that exemplar, sorry, of the, we will take that yes, we will take this set from 1 to n z times. And this space consists of words that are infinite in both sides. So words consisting of letters from 1 to n. And the measure on this space is a product measure on X, and we define Bernoulli shift as a map T that is a shift to the right. So this is right. This is a right Bernoulli shift, and what it means is that we move the start of this word, so the null's element of this word to the right. For example, if we had a word that if we had the element 0 that was 0 and the element 1 that we called 1, now we have the zeros element which is 1, and the element number -1 is now 0. So this is a Bernoulli shift with weights lambda 1, lambda 2. And now we will consider a partition which consists of cylindrical sets where a set so where x1 is all those words that whose zeroth element is 0. X2 is the set of words whose zeroth element is 1, and etc. So the probability of now here we can easily see that Xi is a generating partition, and we get that the entropy of this dynamical system of a Bernoulli shift is a sum of function eta from lambda k, a sum from 1 to n. So I think that it is quite clear that this partition is generating. I can probably explain it a bit more clearly if you ask me. So if you don't have any questions, I think I will proceed. If nobody. Okay. So then we have a theorem by Ornstein that states that Bernoulli shifts with the same entropy are isomorphic. And this example is very important because of the following notion. So firstly, I will define a factor system of a dynamical system X mu T. So we will take factor as we discussed earlier on this lecture, and but now we will need a T. We will need Xi to be a T invariant measurable partition. So we add this property that Xi is T invertible. So now we have a factor system, and a theorem by Sinai states that for an ergodic dynamical system with the entropy greater than 0, there for any h that is less than this entropy, there exists a factor system which is isomorphic to the Bernoulli shift with entropy h. So now I would like to discuss some of the properties of dynamical systems, of dynamical entropies. So firstly, the first property is that the dynamical entropy of T to the power of n is the absolute value of n times the entropy of the dynamical system T. Then we have a property that if we have a factor system, then the entropy of the first system is greater or equal than the entropy of a factor system, and then The third property is that if we have a t-invariant subset of x, that is y, we can express entropy of t in the following way. So we multiply the measure of y by the entropy of the restriction of t to y, and then we take the measure of the complement of y to x and multiply it by the entropy of the restriction of t to this complement. So another property is that if we take another dynamical system, we can take we can compute the entropy of a product of the systems and just as a sum of two entropies these systems.
So may I ask a question about about part 3? So do you assume here that the complement of y is also t-invariant? So you write the restriction of t to the complement, so that's why I'm asking. So of course you can restrict t to y, but what is the restriction of t to the complement?
Yes, I think that I mean that that the complement is also t-invariant.
Oh, okay, thank you.
Okay, so next, so this is the properties of dynamical entropy, which I'll probably discuss later, and then we will need to discuss properties of entropy of finite partitions, finite measurable partitions for a bit longer. So they're quite similar to the properties that we discussed before for conditional entropy, and they're derived mostly from those properties and from the subadditivity of entropy. So now we have the following. Firstly, for a measurable partition xi, the entropy of xi is always less or equal to logarithm of n, and equality holds if and only if a measure of each part of each element of this partition is exactly 1 divided by n, 1/nth. So the next property is that we can rewrite so this property should be called, okay, if we have an entropy of union of three partitions xi, zeta, and theta plus entropy of zeta, we can it is less or equal than entropy of xi of the union of xi and zeta plus entropy of the union of zeta and theta. The next property is just the subadditivity of entropy, and the equality holds if and only if xi and zeta are independent. And the last property is that we can that if we have two partitions, no, if we have two collections of partitions, one of and for each pair xi k and zeta k of this partition, we have that zeta k is less or equal than no, xi k is less or equal than zeta k, then we have the following result that you can see on your screens. I think I won't read it out loud, but I think it is quite clear. So this is one of the properties that I would like to, I mean, these four properties are will probably be proved just I think in 10 minutes. And now I will proceed.
Can I ask?
Excuse me? Is somebody asking questions?
Yes. Can you? So Ash, it's entropy. Yes, I want to highlight the difference between this entropy and conditional entropy.
This entropy and so here we just here I'm discussing just this is the conditional entropy, but where the condition is that the other entropy is just trivial. So here we so the definition is just the same, but we could write in each case. So the condition that we have another entropy that is just that consists of not entropy, sorry, partition. So we can write another partition, but this partition is trivial and it consists just of x, one element x. So here so this is in each of these cases we are having the conditional entropy, but in a trivial case with so with no restrictions. We don't restrict this algebra anywhere. Is it clear?
So we don't have restrictions and we have such entropy. However, the definition of this entropy, which you showed earlier, is not clear.
No, I think that
it's okay. Small h is difficult on the 9th slide.
On the 9th slide, So
we have such definition, but it would be good if you also say about why we define so as a limit such.
So you ask me why do we define this?
Probably some motivation for that.
Okay. So so as I understand this as so I understand this follows that we take a partition xi, right, and look at its entropy, and then we would like to take the average of entropy for xi and each of its images. So we take xi, then we take image of xi, then next image and next, and we take so infinitely many. No, we don't take infinitely many, but we have this limit, right? We take many images of xi, and then we take the average of the entropies, and we call this thing the entropy of t and xi. So how the entropy of how t is how t acts on xi. So at least this is how I understand at this moment.
And you just arbitrary measure preserving transformation of the backspace.
Excuse me?
T is just arbitrary measure preserving partition function.
Yes.
But we will have limit. Limit. We will have limit of taking compositions T.
So you're asking
So
why this limit exists, right?
yes. So as I understand, we take t from C, and t is transformation,
Mm-hmm.
and we get infinite many transformations.
Mm-hmm. Firstly, I think that we say that T is measure preserving, and therefore, when we take T from each element of Xi I, right, we have so the measure of the image is so I mean, yes, the measure of the pre-image is the same as the measure of the image, and so this is what we should remember. And then we have already discussed. I can discuss it just a bit longer. That this part, that this function, is subadditive, and so we can take. So if we take n plus m in place of n, right? If we have here n plus m numbers, then we using the subadditivity can split it into two halves, and we can say that h of this thing from t to the power of 0 to t to the power of n plus m minus 1 is less or equal than h of the union of t0 to t n minus 1 plus we take another. So we are making we're using this we're showing that this property holds. I don't know if you see my mouth, my computer mouse, I mean. I'm showing that n plus m's element is always less or equal than the sum of n's and m's element. So first part is here from, so it looks exactly like this thing, and then we take h from t to the power of n to and the union of everything to t to the power of n plus m minus 1. Right, so and then we should show probably that this is, so this second part has the same entropy as h from t to the power of 0 to t to the power m minus 1 to make this inequality. And then we use this result, this theorem, to achieve that if we have this property for h, and we do have this property for h, then we can apply this thing and get that if we divide h by n, then the limit of such sequence exists and coincides with the infimum of the sequence. Hello? Has it?
Vladislav, are you satisfied with the answer?
Okay, it's better.
Okay, so as I have described, so the definition of a capital H is just, excuse me, I'll find it, is just this definition, but in this case we're taking zeta that is a trivial partition, so this not very complicated. Okay, and now I would like to go further and discuss with you topological entropy. So now we assume that H is a homomorphism of compact separable space, and we call the pair X and T a topological dynamical system. Then we take U, which is an open cover of X, and we call and we define a function n from U as the minimal number of elements of U needed to cover X. We should know that if we have two different open covers, U and V, then the union of these open covers is formed by the intersections of the pairwise intersections of all of its elements. And obviously, n from the union of U and V is less or equal than the n from U times n from V, and we define the topological entropy in the same fashion as we defined the dynamical entropy before. We take the limit of the following function, and then we define topological entropy as the supremum taken over all open covers. I think that all open covers of X, and this is how we define topological entropy for a topological dynamical system. But again, this is not a very practical way to define this, and therefore we need to give another definition which uses spanning and separating sets. So now I will define spanning and separating sets. Now first I will define that yes, I will define what are separated and spanning subsets of X. So X is a metric space and D is a matrix on it, and we take epsilon which is greater than 0, and in this case a subset F of X is called an epsilon spanning with respect to T if for every X there exists Y in F such that maximal distance between t to the power of k x and t to the power of k y is less than epsilon. And the maximum is taken from 0 to n minus 1. And we call a subset F and epsilon separated if for any x and y in F which do not coincide, we have that the maximal distance between t to the power of kx and t to the power of ky is greater or equal than epsilon. Now we say that we call this SP and epsilon the minimal cardinality of an epsilon spanning set, and we call SR and epsilon the maximal cardinality of an epsilon separated set. And if U is an open cover with a Lebesgue number epsilon, and Lebesgue number is means that for any open ball of radius epsilon, so that any open ball of radius epsilon is contained in one of the elements of U, right? And V is an open cover with a diameter less than epsilon, which means that for each element of V, the maximum distance between the supremum, I mean, of distances between points in each element of V is less than epsilon. Then we can check. Oh, I'm sorry, I have forgotten to put a slash, and it didn't compile well. So one can check that these two inequalities hold. Three inequalities actually, and from this we can derive the following definition for topological entropy. So here on the slide we have definition using both separating and spanning sets. And this is how we can define a topological entropy as a measure of the distortion of iteration of t. So again, we have a list of properties. Probably I won't prove all of them, but they're very similar to the properties of dynamical entropy. The first one is exactly the same as we have discussed for dynamical entropy. And then we have, the same property for a factorial map, and the same properties for a subset, I think. No, it's not the same. Now we have for any subset that is closed and T invariant, we have that topological entropy of T is just greater or equal than the restriction, than the topological entropy of the restriction of T to Y. And if in addition we have that Y is open, then we know that topological entropy of T is a maximum of topological entropy of the restriction of T to Y, or the topological entropy of the restriction of T to the complement of Y. Again, we have a property for a product of two dynamical systems. Firstly, we have that. So firstly, we have that the topological entropy of the product of T and S is the sum of topological entropy of each of these dynamical systems. And lastly, we have a property that if we have an open cover U such that it's such as the dynamic diameter of the union of n images and n pre-images of this open cover with respect to some compatible matrix tends to 0, then we have that topological entropy of T is equal to H from U and T. Next, I think that, yes, we have a theorem called Variational principle that connects the definitions of topological entropy and dynamical entropy. So actually, for every topological dynamical system, the topological entropy of T is equal to the supremum of dynamical entropy of T taken over all T invariant probability measures. So then we would like to use this principle a bit more and So it happens that for uniquely ergodic topological system, we can. So we have just one t-invariant probability measure, and therefore dynamical entropy is equal to topological entropy. Then we have a theorem by, I'm not sure how to pronounce these surnames, but I think it's Gibret and Krieger. They state that every ergodic dynamical system has a uniquely ergodic topological model. And I think that to finish this part about the dynamical about topological entropy and its connection with spanning sets, we will define. We'll show that we can define dynamical entropy using spanning sets. And to do this, we will do the following. We will have a topological dynamical system, and we will take a t-invariant probability measure mu, which in this case we assume to be ergodic. So as I understand it, this we don't actually need it to be ergodic, but it just makes the proof much easier, and therefore we will have just a bit weaker form of this statement for ergodic t-invariant probability measures. So now we define an epsilon delta spanning sets for T mu as the set of all x's, such that there exists a y from a subset F with the following property. Now we denote by SP and epsilon delta the minimal cardinality of an epsilon delta spanning set, and for any delta we achieve the following equality. So, and this will be the definition of dynamical entropy using the cardinality of the minimal cardinality of spanning set. So now I think, oh yes, and to prove this, we will use the following theorem. It can be easily applied and to achieve this result. So this is a theorem of Shannon, Macmillan, and Breiman, and it states that if we have an ergodic dynamical system and a finite measurable partition of X, then for any element of X and a natural number n, we will denote by I and X the element of the following partition of the union of n minus 1 images of this partition containing X, and then we get this convergence that holds in mean and almost everywhere. So by applying this theorem, we can prove the result on this slide, that measure entropy can indeed be defined using spanning sets. So the next part of this lecture is about partitions of unity, but I would like firstly to tell you something about some of the proofs of the properties that I have discussed before, if you don't mind. Okay, I think we can I think we can go to prove something. Now I will finish the demonstration of my presentation and use a whiteboard and write some of the proofs on it. So give me one moment. I'm creating a new whiteboard. And now I will share it with you. So, so I think this is my whiteboard. Do you see it?
Yes, yes.
Hello, okay. Thank you. So I think that it will be interesting to, do I understand it correctly that I have about 15 minutes left?
Yeah, you still have 15 minutes.
So, okay, in 15 minutes, I can discuss some of the properties. So the reason that I go to prove something and not discuss the last part is that I think that probably the last part will quite naturally be connected to the beginning of the second talk, if when I will tell you about it. And therefore, I think it is more useful to discuss some of the properties. And probably I will start, so I will try to write something. Так. So can somebody see what I write?
Looks like the word properties. Properties of
Conditional. So properties of conditional entropy, right? So I can prove something about this part, or I can rather prove properties of partitions. And would you like to choose which one, which of these propositions I should prove? So I have two variants. First is the conditional entropy, and the second is just entropy. Entropy of.
It's up to you. So
Okay. Okay. So I think that probably conditional entropy is not what we will use the most in the future, right? And therefore, I think that we'll just leave them without proof. And if somebody wants to look up the proofs, they can just use the book from which I base the talk. And now at the moment I will prove something about properties of H xi, where xi is finite partition. Finite partition. I won't write it. So finite measure preserving partition, but I won't write everything. So I need to find it. Okay. So the first property that I would like to discuss is that if xi is consists of n elements, xi1, xi(n), then entropy of xi is less or equal than logarithm n. Proof. So So the proof is as follows. So we are using the fact that eta, the function eta, which as we remember is defined as eta from t, is defined as minus t logarithm t or 0. And the first part is in the case where t is greater or equal than 0, and the second is when t is equal to 0. So this function is strictly concave, and therefore we achieve the following inequality. We will have a sum of eta from measure of x case, which is less or equal than n new, sorry, eta not new, from the sum of k elements, mu xk n, and this one is equal to logarithm n. So what I'm doing here is I multiply and divide by n, and I use an inequality. I think I'm using the Jensen inequality here. I mean, in this part. And I achieve this result. So the second part of our proposition is that, I'll take it here. The second part of my talk, not of my talk, of this proof, is to prove the second property. And the second property of measure entropy is as follows. We take an entropy of the union of psi, delta, and theta, and the entropy of zeta, and we state that it is less or equal than the following sum: h, xi, and zeta plus h, zeta, and theta. I hope you can understand my writings. Is it clear?
Yes.
Okay, thank you. So, and we are using, so I think that we are using here the property of conditional expectations. So, and we achieve the following result. We achieve that h, xi, zeta, and theta minus h, xi, and zeta is equal to h theta with respect to psi and zeta. So this is a property of conditional expectation, and they have discussed. So in this property we had, so we just so to see that this is the same property, we should put this thing, this part, to this part of the inequality, and this sum, the new sum, will be equal to h of the union of xi, z, and theta, and this is exactly the property that we have discussed for conditional expectation. Then the second thing that we need to do is to see the following property. So apply this property again and achieve it for the following union. We take zeta and theta minus h zeta, and it is equal to theta with respect to zeta. Again, this is the same property, and this is the way that we can express function h of the union of zeta and theta. We can just express it as a sum of h from zeta and from the conditional expectation of theta from zeta, which so, and these two ideas, and so these two inequalities, the first and the second one, not inequalities, equalities. If we apply it, so we can easily see that they indeed prove the second property of measure entropy. So if we cannot, so if somebody cannot see it, you can ask me now. So, well, I think that this is rather clear. So now we have to move to the second part and to the third part, to the third inequality, and probably we'll stop there. We'll prove the third property of, sorry. We'll prove the third property of entropy of measurable partitions, and here we will stop our lecture for today. So I'm having this property that the following inequality holds for partitions Xi and delta, and the equality holds if and only if Xi and zeta are independent. So we have equality if Xi and zeta are independent. So, and how do we prove it? So now to prove it, we should show the following. So we have, as I have discussed several times today, we can write the following equality just as in the property before this one. We can take, we can write it as a sum of h and h Xi with respect, zeta with respect to Xi. Okay, and we have to show that this thing, the second part of the sum, is equal to h of zeta, if and only if these two partitions are independent. So, how do we prove it? Well, let's suppose that Xi, no, not Xi, zeta is as usual just this partition of n parts, and from the fact that eta is strictly concave, we can, no, firstly we will just use the definition of the conditional entropy and write the sum of integrals on x of eta conditional expectation of characteristic function of xk the mu, and from the fact that our function is strictly concave, we achieve that we can change eta and the integral, and have the following. And have the following sum, which is exactly, it is easy to see that it is just a sum of new from measures of each xk. So, and the equality will hold if and only if the conditional expectation is a constant for each k, and therefore we will need sorry, where I am. Okay, we will need the following equality. That the conditional expectation is equal to the measure of xk. And these conditions means exactly that xi and zeta are independent. And therefore, we achieve the part about independence. So I think that we will not prove the third, the fourth part of this, the fourth property. So we have proved three properties of measure entropy, and I think it will be good to proceed from this part next time, when I will tell you more about how to generalize these notions, how to generalize the idea of entropy to non-commutative cases. So, thank you for listening, I guess.
Thank you very much.
Mm-hmm.
So please, questions and remarks.
Do we have any analog of temperature?
Excuse me? Can you?
Do we have
speak?
any analog of temperature? Because in usual thermodynamics, entropy and temperature usually together.
Okay. Probably. So if you don't mind, I'll probably think about this question while I'm preparing the second talk, okay? So at the moment I don't have, if I understood your question, I don't have answer at the moment, but I'll think about it.
Thanks.
Maybe simple remark that inequality from property 3 follows immediately from property 2 when we take zeta be empty set. Maybe I missed something, but is it true that today, in definition, we have function minus t logarithm t? Is it true that today, in fact, we use only that it's a continuous, strictly upconvex function which vanishes at 1 and 0?
Yes, you're right. Today we use only this part, right?
Okay, thanks.
So I would probably like to hear some remarks from Alexey Yulievich, if you have some. So if you have some ideas what I can change in the second talk, maybe try to go more faster and just do not pause for a long time for
well, in my point of view, there is no reason to go faster. And also, well, I don't think that that many of us are specialists in dynamics. So maybe it would be good if you add some motivation on where these definitions come from. So you gave us a lot of formal definitions and properties, but it would be very interesting to know some, well, maybe motivations from physics, some from thermodynamics, some from information theory. So if you spend 10 or 20 minutes, as you like, to explain these things to us, that would be good. So in general, it would be good if you make your talk a bit more popular,
okay.
if it is possible.
Okay, yes, but still I think that it was useful to define some simple definitions,
Of
just
course.
so that we're all on the same page here. Okay, so I'll start next time with some more motivations and yeah, okay.
Okay, thank you very much.
Thank you. Thank you for listening.